Okay, so we are going to attempt to get through this PowerPoint today. It's Friday. Uh, I did not get very far with y'all yesterday, so I'm going to try to get through this extremely quickly. Where we left off yesterday was the beginning of section 12.4. How do we study past climate change and make predictions? And I talked to you about the three big concepts in studying past climate. So we have instrumental record, where humans have directly measured things like temperature or carbon dioxide. So if we had the technology and the instruments and people were measuring them at that time and writing it down, that's part of the instrumental record. Then you can go back into the historical record, and this is going to be more like memory. So like I said, you have like an assistant to a king or a queen, and they write that, oh, it's been an unseasonably hot summer. And so you can go back and you don't have direct temperatures, but you can know that that summer, according to someone who's relatively trustworthy, was hotter than previous summers on memory. And then you go into the paleoproxy record. Paleoproxy is something that a lot of different people do right now. It's very technical, it's very complicated, and there's lots of different ways that you can do it. And basically, what the proxy part means is you are getting measurements today from things that have information about older times, paleo times, before history. And so the things that they're referring to are things like tree ring studies, which is called dendroclimatology. Dendro is like a prefix for trees, and climatology obviously is the study of climates. And so you're studying tree rings and how trees form as living things. They're greatly going to be dependent on the amount of oxygen in the air, the amount of carbon dioxide in the air, how much rain falls. They're going to be susceptible to different new chemicals that get introduced into the atmosphere. And so by studying their rings and taking samples of the actual growth of the tree, you can understand and learn a lot about times where humans weren't necessarily recording temperatures and seeing what the environment was like. Same thing with sediments. When we drill into rock, we can pull up a large core of rock and sample that. And the way that the sediments fall, the gases that they trap, whether your irons are rusted or not, can tell you a lot about what was going on in the environment at that time, and the atmosphere as well. Same thing with ice cores. Ice cores are going to be very similar to sediments, except instead of drilling into rock, you're drilling into ice. You do have to handle them a little differently. They have some pictures here. Notice that the rock guy is just like t-shirt with barely like some gloves on. The ice guy is like fully suited up, and all you can see is his nose sticking out the front. And the reason is the ice is much more difficult to keep that as almost like the time capsule that we imagine it being. Once you start to cut it open, if it gets down below freezing, you're going to lose all the data that you had. And so even right now, as he's cutting through this core, you're losing some gas that was trapped in between those pieces of ice. And so you have to be very careful about how you process your ice cores, and how you do your work. Where with your sandstone cores, you got to be a little less cautious. Basically, you just want to keep everything in order from top to bottom. But beyond that, you can do a lot of different things to it. You can even see here, he's drilled little holes out and taken samples out of the middle of the core. If I go back up real quick, they just have a nice illustration on the tree ring dendrochronology. And this, if you can imagine, you find one tree, even if it's a really old tree, it's not going to give you the whole story. And so what we want to do is, as we sample different trees, we want to line up different events in those trees' lives to other trees. And so you can see, while this tree had this event, which is just a sequence of lines at certain spaces, and this was when the tree was very young. So right when the tree was born, right near the core, this event happened. I can find another tree where this event happened towards the end of that tree's life. And so almost by making like a mosaic picture or a panorama, I can line up these different events and get a bigger picture of the timeline. So they show it here with three. If you get a bunch of different trees, you can get a very long timeline and kind of build this entire history of dendrochronology. So they use a little bit of everything to try to build this like timeline. Along with this are some other types. Pollen is crazy, crazy interesting, if you ask me. If you've never seen pollen in a microscope, it looks insane. And if you think about it, anyone with allergies can attest to this. Pollen goes everywhere. You don't have to be outside like shaking a tree to get allergies. You can stay inside all day and your nose is going to run and you're going to sneeze. And so the truth is, when you look through historical physical things like rocks, sandstones, you can look in ice cores, pretty much anywhere you look. If you look small enough and you look hard enough, you will find pollen. And that pollen can tell you what kind of trees were living at that time, what the environment was like, what the wind patterns were like. They can determine a lot of information from pollen, and it's just super, super interesting and super intricate. There's not a lot of people I know that would love to like hunt down individual pollen grains. It's literally like a needle in a haystack. And so I salute the pollen people, and I'm always interested in the work that they're doing. Corals are going to do something similar. Obviously, these are very limited. Corals only grow in a very specific environment in the ocean. That being said, when these corals die, they essentially turn into a rock. They turn into a rock record. And so we can go and look at old corals, where they're at, what kind of rocks they're surrounded at, and that can help us build another part of the picture. Carbon-14 dating, this works really well. The only limitation is it's got to be on something that was living. So one of the good things is if I find an old tree, I don't really know where that tree fits into my sequence, or it's well dead and I don't really know what time it lived in, I can kind of line this up with my carbon-14. I can go into that tree and get an exact date, or at least an exact date plus or minus some bar of error that tells me exactly when that tree lived, and so I can find a better place for it in the timeline. And then carbon dioxide levels. Obviously, we are interested in carbon dioxide levels right now because of its use as a greenhouse gas, or its effect as a greenhouse gas. And so we would like to go back and see what carbon dioxide looked like in the past. So here is a good map right here of CO2 levels that we have directly measured since 1960 all the way up to 2010, maybe 2011, it looks like. Before 1960, we didn't really have the instrumentation to measure CO2 levels, but now we do. And you can see overall you're trending, but you can also see what is like the shape of this line. What is the line doing as it goes up? It's got the zigzags, right? What do you think the zigzags are? Why would in 1 year would CO2 levels go like up and down, up and down? What is CO2 part of as a natural cycle? Huh? What'd you say?
Decomposition.
Oh, decomposition? Yeah, decomposition. I'm thinking more like natural plant cycles. It's photosynthesis, right? Yeah, plants taking CO2, they put out oxygen. And so are there cycles in a single year where plants are active and more active? Yeah, and so I'm not 100% certain. I'm not like a CO2 scientist, but this up and down squiggle, at least every single year, seems to me to be seasonal. In the summer times when plants are more active and everything's blooming and doing its photosynthesis thing, probably have a lot less CO2 in the atmosphere. And then wintertime when all the plants die off and they're doing less photosynthesis and respiration, you're probably going to have a lot more CO2. And so that cycle is probably what you're seeing on the up and down, just your standard yearly seasonal cycle. And then overall, you can see the increase that's happening. Here, they're looking at atmospheric CO2 trapped in glacial ice bubbles. So we have measurements all the way back to 1960, but we can go back even further than that if we find the right ice bubbles that have trapped air from that particular atmosphere at that time into the ice. And so we can see the CO2 levels all the way back to 1500 roughly, maybe even further back, depends on where we're getting our ice from. Let's see. Air temperature changes. correspond closely to atmospheric CO2. So what they've done is overlaid our temperature graph, which is in green, with our CO2 graph, which is in red. And we see that as your CO2 goes up, your temperature also goes up. As your temperature goes down, your CO2 also goes down. So, if anybody is ever like, well, CO2 doesn't necessarily mean it's going to get hotter. Yeah, it pretty much does. Let's see. Global climate models. I've talked to y'all about models several times. As a student of mine going out into the world, have a healthy respect for computer models and math models. They do a lot of amazing things. And if you get into some sort of science and you're not using computer models or math models to try to advance your work, you're probably behind everybody else. Math models and computer models are a huge, huge deal. You use them in everything, and it's your way to basically simulate the world. To say, well, what if this happened? Well, you don't have to wait for it to happen in the real world. You can make a computer world and make that thing happen and see what the effects would be. It's not always perfect, but it does work really well. The best example would be weather. When you look at how accurately we can predict weather, I was listening to The Ticket this morning, and they were talking about how, 100 years ago, you walk out your house in the morning, you have no idea what the weather's going to do that day. It could literally hail, like golf ball size hail on you, or it could be a perfectly sunny day with no clouds at all, and you would have no clue. And today, they get some stuff wrong, but you pretty much know exactly what the weather's going to be every single week. Like, they tell you when it's going to rain, how bad it's going to rain. They've even gotten good at knowing whether a storm's going to have tornadoes or not, 3-4 days out. That's pretty amazing. And almost all of it is done with computer models. They put all of the data in, all the temperatures, what directions the wind's blowing, and they tell the model what's it going to do tomorrow, what's it going to do the next day, and they just run a bunch of them. And if you have a whole bunch, a high percentage, 50, 60% are it's going to rain right here in the next 2 days, then you can probably trust those models. So we do the same thing in climate. We build these very complicated digital worlds, and we mess around with the atmosphere. We mess around with the CO2. We mess around with the methane, and we see what it does to the atmosphere and to the environment, and it gives us a better understanding of what's actually happening. So let's see. Global climate models, what we're trying to do is predict that change. We're trying to see what's going to happen, where it's going to happen at. One of the things I will kind of point out to you is that with change, it's not always changing the same way for everybody. One of the things that I learned pursuing degrees in oil and gas is that one of the reasons the Middle East has a crap ton of oil. Literally, I cannot exaggerate how much more oil they have than everyone else in the world. They have oil fields right now in the Middle East that they're we're not going to drill that. That's just too much work. It's not worth it financially. We'll just leave all that oil in the ground. And that oil field that they're just decidedly not drilling right now, if it were in the United States, would be the largest oil field we've ever had in the United States ever, period. So they have an immense amount of oil. They're really not ever going to run out anytime soon. Geologically, they're in the perfect place. Now, the Middle East is desert, right? It's like the desert. That's the entire environment up there. They do have rainy seasons. They have different stuff. But pretty much that entire area is desert land. And then you study the history of oil and gas, and you find out that the reason they have so much oil and gas is pretty much from this point back in history, they have been a tropical area. And it didn't matter what all the other continents were doing. For most of the Middle East's history, it has been a tropical paradise with lots of trees, perfect weather, great water conditions, and lots of moisture. And that's the way their oil and gas formed. And now they're not that way. They're this desert area. And so when we talk about global warming and temperature changing and sea level rising, Some areas are going to get worse. Some areas are going to get better. There's a future where the Sahara Desert is like a tropical rainforest. And it doesn't necessarily mean that that's a good thing. Deserts are great areas. They have their own ecosystem. And if that were to be replaced with something else, it would be a huge, huge change and cause a lot of problems for a lot of species, including humans. So it's not just about predicting bad stuff. It's about predicting everything and understanding all the different ways that your environment can change. And like I said, some people, I don't know everybody, I don't really even know who, are trying to have a very forward, futuristic look on things. And the truth is, if humans want to be here for thousands and thousands of years in the future, 10,000, 20,000, 50,000 years, the world that we live on today is going to look very, very different. And we need to be able to adapt. And that's one of the things I think scientists do kind of worry about now. We adapt when we have to, but historically, when someone asks you to adapt or do something, we seem to be kind of hesitant to do it. When push comes to shove and it's all about survival, got it. But if we don't feel that fight or flight kind of fear about our survival, when someone's like, hey, if you do this, it'll be better for you tomorrow, we're more likely to be like, nah, I don't know. And so it's really important that we have a full understanding of the climate, what's going on with the climate, and what we're doing to it. Because, we're not going to live past 80, 100 years. Maybe if technology gets better and we all take care of ourselves, we're like 120. So it's not our problem. But at some point in time, it's going to be somebody's problem. And they're going to wish that the people before them had thought about it a little bit more and understood it a little bit more. So we got to do our best here. So what are we looking at? Modeling climate. They're showing temperature increases here from 1900 to 2000. This is compared to the average. So this is change in temperatures. And I don't really know what they're showing over here. It's just like a model of the Earth. But let's see. No, I don't know. Oh, this is actually pretty cool. One of the things they're pointing out here is they have some really, really huge volcanic eruptions marked on this temperature map. And what they're showing, every large volcanic eruption is associated with a temperature drop. Because of all the ash that's spewed out into the atmosphere, it blocks out the sun, and you see a direct correlation to drop in temperatures there. And so that's a pretty interesting thing on the map. So now, 12.5, global warming. They're going to make the case for global warming, and I think there's a lot of slides here, so I'm going to kind of blow through them pretty quickly. So there's been an observed increase in average temperature of land and ocean during the past 60 years, probably resulting from burning of fossil fuels. Both human and natural processes are contributing to warming. So that's the key here. Good climate scientists will not deny that we naturally warm and cool, and that we're naturally in a warming state right now. We're leaving a regular glacial interval and heading into an interglacial interval. So we should be warming up. That being said, there's no denying the amount of pollutants that we have put into the air in doing our industrial kind of processes. And there's no denying what those pollutants do to the atmosphere and how they react. And so the only real argument that we're having is what are we going to do about it? How much burden is our economy going to take? How much burden should individuals be responsible for in trying to change what we're doing as an entire society or as an entire people? And that ultimately is like a pretty fundamental argument. Like, is it society's job? Is it the individual's job? Does all the individuals have to contribute to get the society to change? It's a little bit of everything. So Earth's temperature depends on, and we talked about this in the other chapter, it's really about sunlight received versus reflected. It's your sun budget and how much energy you're keeping versus how much energy you're kind of letting go back out into space. And so we call it the energy balance or the energy budget. And we try to keep track of exactly what's happening here. And the truth is, the Earth, while it gets pretty much 100% of its energy from the sun, we don't need all the energy the sun gets us. We reflect quite a bit out into space from clouds. We radiate quite a bit of radiation out into space in long wave form. And so we have a system where the Earth kind of cools down as the sun is heating us up. And that's why we do kind of worry about these greenhouse gases. And it is kind of like a catchy term, greenhouse. It doesn't maybe hit quite as well down here in Texas, because do we really use greenhouses in Texas? Not a lot. And in general, we kind of use them from different purposes. It's not necessarily like a keep things from freezing in the winter kind of thing. We do every once in a while, but if you've built a greenhouse in Texas to keep your plants from freezing in the winter, it's kind of frivolous because you're only freezing a couple days. So greenhouses, like it's not getting the same ring for everybody else. But I think the point is looking at the budget and knowing that we get too much heat from the sun to be comfortable, and we require a certain amount of heat to be able to leave. Well, if you start to talk about greenhouse gases, they're the things that's going to keep that heat in. It's like, driving around in the summer with your windows rolled up, with no AC on, obviously. The AC is on and the windows are up, that's okay. But in the summertime, you got those windows up and that heat that's been in your car can't leave. It stays very, very hot. It's like an oven. If you just crack the windows a little bit and let just a little bit of that air out, it can be a world of difference. And so that's kind of a metaphor for what's going on. We're really worried that if we get some things that start to trap heat in here, it's going to get really hot really quick, and we're going to have some issues with it. So lower atmosphere is much warmer than if all this radiation escaped into space. So they're talking about the heat here, the heat budget. You can see what we're losing on the sun's energy and what gets reflected back out. And the point is, we wanna not get too hot here. So greenhouse effect is a natural and necessary process. The Earth would be 33 degrees colder without it. All surface water would be frozen. Little life would exist. And this is a history lesson we've had to learn over and over again. Humans like to change things and keep things the same, and often we do that without thinking about stuff. Classically, we will see like a tiny cute animal not thriving and dying and getting close to extinction, and because it's cute, we're like, we got to save it, we got to save this animal. And the first question should have been, is it our job to save this animal? Like, are we the ones that killed this animal, or are we just saving it because it looks cute? The second question is, if I save this animal, what kind of problems am I creating for other animals? And is this the right thing to do? And the truth is, not all the time are you making the right decision. And so, if we didn't think about this in a big kind of way, we might just think all greenhouse stuff is bad. We need to get rid of this altogether. The colder we get, the better. We just need to get rid of the heat. And that's not true. You want this balance. You want to keep things as close to natural as you can. And I think a lot of people are starting to think that humans should start to take a more hands-off approach to the environment. Instead of messing up everything and trying to fix everything, we should back off of both sides and just do our best not to screw up everything. And then when we see something that's bad that doesn't really have anything to do with us, do our best to just leave it alone and kind of let nature do its thing. It's hard to do, but it's probably something that we should look at. So most of the natural effect is from water vapor. This is your greenhouse effect that they're referring to. So human activities have increased the amounts of greenhouse gases. This is called anthropogenic greenhouse gases. Anything you see that word anthropogenic, it has to do with humans. Anthro is humans. Let's see. Carbon dioxide accounts for most of the anthropogenic greenhouse effect. They are starting to look at how bad methane is, because methane really works a lot better as a greenhouse gas than carbon dioxide does. And so, although we produce a lot less of it, it is a pretty serious contributor. So here's your CO2 rate of increase per year is about 0.5. Relative contribution is about 60%. They're saying of greenhouse gases. For CH4, you're at 15%. And if you remember back to the amount of percent they are in the atmosphere, CH4 makes up a lot less of the atmosphere for such a big contribution to greenhouse gases. So global temperature change, they're saying over the last 800,000 years, so close to a million years, low temperatures coincide with major continental glaciations. High temperatures coincide with interglacial periods. So when it's cold, we have ice. When it's hot, we don't have ice. In the last 150 years, the last major interglacial period, the Eemian, sea level was 4 to 6 feet higher than today. And so we know not even that long ago, really, 150,000 years ago, I'm not super up with my human evolution chart, but humans were around. We were doing stuff, right? If you looked at a map of what the world would look like today with a 4 to 6 foot sea level rise change, the coastlines look very, very different. If this happened today in a relatively short period of time, which it wouldn't, it would be extremely devastating for us as far as economically and locationally, where people live, migratorily. That's not really a word, but so in the last 18,000 years, which is really, really recently, a cold interval called the Younger Dryas occurred about 11,500 years ago, followed by a warming to the Holocene maximum. Recent cooling called the Little Ice Age in the 15th and 19th centuries. So we're just leaving behind the last ice age, and we're going into this interglacial period. So things are about to naturally get hotter. If we continue to pollute and cause greenhouse effect to be worse, will we see something worse than this 4 to 6 foot rise? Will it be higher? Will it be roughly the same? If all the ice is melted anyways, maybe it won't matter. Maybe the maximum sea level is the maximum sea level because that's all the water we have. But that probably isn't something we really want to test out. So this is just a chart to show you those last three segments that they went through. So you have the 800,000 year chart, you have the 150,000 year chart, and then the 18,000 year chart, just kind of showing you where we're at, what we're looking at. So note that on all three of these charts, we are not at the maximum temperature that we've ever been at. That being said, we're not near the middle either. We're already up at the top, and we're still headed up. So then they go to the last 1,000 years, several warming trends. They go into the most recent warming, which is AD 1100 to 1300. Last 140 years, since 1750, warming trend begins until the 1940s. 1910 to 1998, global temperatures rise. Most of the increases since the 1970s. The 1990s and first decade of the 21st century is the warmest temperature since monitoring began. So another temperature map for the 1,000 years and the last 140 years. And then they go through a couple cycles, the Milankovitch cycles. Nature changes in Earth's orbits, tilts, and precession. Explains some changes, but not the observed large-scale changes that we see from climate. So basically what they're saying is Earth does different things. We get closer to the sun, we get further away from the sun, we tilt a little different way. All of these are going to have an effect on our climates, but not the huge effect that we're seeing. So they talk about climate forcing, an imposed change of Earth's energy balance, positive if increased temperatures or negative if decreased. This is like Burns blotting out the sun in The Simpsons, right? I want everybody to use my electricity. I'll blot out the sun. So we're not to this level yet, but people have considered, putting stuff into the atmosphere, doing different things to try to force climate. I think maybe the most ambitious and crazy and like worrisome climate forcing talk recently has been Elon Musk proposing that we nuke Mars to jumpstart the climatology of Mars and get some air back in the atmosphere. So at least they're talking about nuking a different planet and not our planet. So maybe that's a good thing. Let's see. Concentrations of greenhouse gases during the past 2,000 years. And so note that, we don't have direct measurements for the vast majority of this stuff. We're doing paleoproxy records. That being said, you have several different paleoproxy records for different chemicals that were taken in different ways that all kind of align to these much, much lower levels than we have now. That being said, I think I don't know what level we're at and what good it's going to do. We are getting closer and closer to technology that can remove this from the atmosphere. Probably not a great option to choose, but looking at where we're at, we might want to just physically try to start moving the stuff in the atmosphere. I know at the rocket site down in Boca Chica, Texas, they just set up a large industrial piece of equipment to pull methane from the air. And so it literally sits in the parking lot right by the building where they build the rockets. And as the air filters through the building, I'm sure it's some complicated mechanism that deserves more justice than I'm about to get it. But it basically pulls methane out of the air, compresses it, and turns it into liquid form. And they're going to take it literally right down the road and pump it in the rocket. And so this is a way for them to buy less methane from manufacturers, but also to remove some of the methane that they're putting into the atmosphere by doing all this testing. So I will point out it's not altruistic. He's not really trying to do a good thing. He's practicing technology that they're going to need on Mars to get enough rocket fuel to come back to Earth. Because the big problem with the Mars trip is it's one way unless you can make your own fuel on Mars to get back. Or unless, I guess, you send rockets ahead that are stocked up with fuel, but that'll be kind of difficult. So we'll see what goes on there. Why does the climate change? Lots of different reasons. Your ocean conveyor belt does change from time to time. If your ocean circulations change, you start to get warm water instead of cold water. That's definitely going to change your climate. So they talk about it a little bit in the Atlantic Ocean. They're showing the conveyor belt of ocean currents. Again, this is very simplified. We've seen some more complex ones that show some different interchanges. But in general, your warm water comes from the equator areas and heads up towards the poles where it sinks down to the bottom and cools and comes back around until it rises up at the equator again. So they're telling us, obviously, not everything's perfect. We have some uncertainties, but there's sufficient evidence to state that there is a discernible human influence on global climate. Discernible, they're meaning detectable. Like I can see that influence that humans are making on the global climate. Warming is now occurring, and the mean surface temperature of Earth will likely increase between 1.5 degrees and 4.5 degrees Celsius during this century over the next 100 years. I like these kind of things. When I see people on the news that are like, by 2040, this and this and this is going to happen. I don't think that they're just making that up. I think that they did some sort of science to get there. 2040 is really close. It seems like a long way away. Like worldwide changes, it's really close. And your ability to predict that early is going to be kind of difficult. The further out your prediction is, the more likely it is to happen. And so, we do want to take care of this. We do want to be serious about it. You don't also want to fall to people who are trying to hype you up and capitalize on your fear to kind of get their agenda across. That being said, take it seriously. So the human-induced component, there's just not a lot to argue here. We cause emissions. Every car we drive, every vehicle we run, every plane we fly. I would point out that industrial pollution is going to be a much bigger factor than your individual car. Given the choice, should I recommend an electric car at some future time? Yes. Do you need to go out today and trade in your gas guzzler for like a Tesla? No. What we want to see is we want to see governments and corporations basically incentivized to take care of a little bit of their pollution, and not just be like it's all about the bottom dollar. The bottom dollar is good, but we all got to live here too. We want to make sure that we're taking care of things. So we are producing emissions. They do trap heat, and there's a strong correlation between connection of CO2 and global temperatures. And we want to be aware of what we're doing. So they talk about solar forcing. I think they're basically going to talk about our ice ages that we get that are somewhat correlated to volcanic eruptions. So when you have volcanic eruptions, you're going to block out a lot of solar radiation. And so when we don't get the sun, we're getting a cooling period. And so they have the Little Ice Age. They have the medieval warm period, which corresponds to increased solar radiation. So we're literally getting more sun at this time, less sun at that time. That's going to correspond to our warm and cold periods. Here's your volcanic forcing. When the volcanoes erupt, they put a lot of ash into the air. That's what blocks out the sun. And you can see here the Little Ice Age that they talked about on the last page was due to volcanic forcing. This is just a picture of your volcanic ash cloud. So you can see this is going to block out some sun. Even after it gets dispersed into the atmosphere, every little particle inside here is going to kick back just a little bit more sunlight and make the entire Earth a little bit cooler. So the anthropogenic forcing is stuff that we're doing, things that we're adding into the atmosphere, and I think we've talked a lot about that. So let's see. Potential effects of global warming. Obviously, we've got the climate warming. We're going to see climate change. I think one of the big things is the coastlines. If the sea levels rise, we're going to lose a lot of land on the coast. That's going to cause a lot of people to have to move. Anytime large masses of people have to move, it puts a strain on the food supply in the globe, on the economy. It's difficult for humans to handle large migrations. And so I think personally, that's one of the biggest dangers of global warming, is just having so much of our coastline eaten up by the ocean, and so many people have to move. I mean, just this area right here, if you have like a couple feet of sea level rise, you're talking about millions and millions and millions of people that have to move. The Philippine Islands, the Indonesian islands, and India coastline here, you're talking about countries that don't have like a lot of empty space for people to go to. The United States, like everybody in Florida and the East Coast has to move away from their homes. We have a huge amount of empty space in here. We got plenty of room for people to move around. It's going to be bad. It's going to wreck our economy. It's going to be terrible, but we'll make it. We have somewhere for those people to go. These islands, you have very little available space for someone to just plop a house down and relocate their life. Same thing with India. Your cities are very packed here. Population density is maxed out. Their ability to just pick up their belongings and move down the road is extremely limited. And so they're going to have to spread out into different countries. The movement of people is going to be the biggest effect, I believe, of global warming. Temperatures we can deal with. Rising waters we can deal with. Humans are pretty adaptable. We're pretty resilient. The movement that is forced by that is going to be what really tests our economy, our ability to get along with other people, and to kind of live together on this planet. So, concern, global warming is accelerating melting of the Greenland ice sheet and the mountain glaciers. Glaciers are retreating worldwide. There are a couple that are advancing in certain areas. Like I said, it's never going to be all one way. There's always going to be certain parts of the world that are kind of doing the opposite thing. But yes, in general, the glaciers are getting smaller, which is going to contribute to sea level rise. The Greenland ice sheet, while that's a lot of water, really the Antarctica ice sheet is going to be your biggest one. And if that thing starts to melt, you're going to see a lot of sea level rise pretty quick. So you can see here, You have the 1992 melt extent, the 2005 melt extent, and I assume the white stuff is the stuff that is not yet melted. But, in less than 20, 30 years, you've lost quite a bit of ice on Greenland here. This is a picture. You can find lots of pictures of all sorts of glaciers like this. I don't remember what year this was. This was maybe 50s or 60s. And this is going to be maybe 80s or 90s. And one of the previous PowerPoints that had the dates on them, and I know the dates are in the book, but you can see how much ice has been lost out of this valley. I think technically this is a separate glacier from the one that's up in this valley. This glacier is gone, and the glacier that's up here has receded quite a bit as well. So positive feedback cycles, y'all are familiar with positive feedback cycles, right? Where something like an effect of something just ends up making it worse. And so as your snow and ice is frozen, it ends up reflecting a lot of radiation. So that's helping to keep us cool along with the lower temperatures. The more snow and ice that melts, you don't get that reflection. That snow and ice hits the surface and causes more heat. And so the less snow and ice we have, the hotter we get, the faster we get. And so that's part of your positive feedback cycle as well. Another thing that they haven't really mentioned, what we're finding now, there's a lot of methane trapped in ice. And the more ice melts, the more methane gets released, and that adds to greenhouse gases as well. Let's see, they're talking about Arctic sea ice, climate patterns, El Nino and La Nina, we've talked about a little bit in the weather sections. The 1997-98 El Nino La Nina event, which I remember a little bit. I would have been in high school then, so I think I remember that. Decadal oscillations, PDO, AO, and NOA. These are the oscillations. Precipitation, some conclusions on sea level rise. Wildfires, we've talked about plenty. Changes in the biosphere. Just know that, a lot of stuff is going to change. If global warming continues, it's going to change the environment and the way that the animals deal with the environment. And I don't think we are anywhere close to being done. So maybe we will finish this on Monday.